the James Webb Space Telescope. Named after the NASA administrator who oversaw the Apollo moon landings, this space behemoth is the largest, most powerful, and most complex space telescope ever built. It has been hailed as the successor of Hubble, which itself was instrumental in expanding our understanding of the universe over the last few decades. It has undergone major redesigns, cost $9.7 billion to build, and has taken 25 years to fully develop, construct, and test. There were moments in its decades-long construction where it was very nearly cancelled completely. And yet, with the aid of scientists from several nations around the world, it has overcome hurdle after hurdle. But for all this, it will only last in space for a maximum of 10 years. Why have scientists undertaken the construction of this telescope? Why put all this time, money, and effort into building something that will be, relatively speaking, so short-lived? The answer is because this telescope, in a way unlike any before it, will allow us to peer through time to the beginnings of the universe itself. I'm Alex McColgan, and you're watching Astrum. Join with me today as we explore how this incredible spacecraft will allow scientists to pull back the curtain on the first galaxies to come into existence after the Big Bang. Together we will discover the science and engineering that went into it, as well as the challenges it faced. Because this truly will be a spacecraft that will help us access clues to the universe's origins like no other. The James Webb Space Telescope first began in 1996. NASA at that time had for years been considering a next generation space telescope, or NGST, to help them find the data they desired, and the original plan was to make an 8-meter aperture telescope that would cost approximately $500 million. However, as time went on, decision makers realized that far more resources would be needed to achieve their aims. But what exactly were their aims? Well, the NGST was to be an infrared telescope. Hubble had been functioning since 1990, but its primary range was the visible light and ultraviolet light spectrums. Although it had some infrared detection capability, this was somewhat limited. And why do scientists want a powerful infrared telescope? Well, this comes down to some fundamental facts about the universe itself. Scientists believe the universe as we know it has existed for roughly 13.8 billion years. How it all began is a fascinating question, and one that many have theorized over. Current mainstream theories revolve around the idea of a Big Bang, where all matter existed in a space so small it was effectively zero. Atoms did not even exist at that stage, they would have been too large. Suddenly, everything expanded outwards at once. Matter began to coalesce into atoms, and then dust, then stars and planets, and the universe has expanded and cooled ever since. But wouldn't it be helpful to be able to look back and see for ourselves those first moments of creation, or the formation of those first galaxies? That might give us insights into exactly how all of it happened. The James Webb Space Telescope will either provide evidence for the Big Bang, or completely change our theories, thanks to the way light travels. To a point at least. While light is blindingly fast, it's not instantaneous. There is a tiny time delay between when light is emitted and when we see it. Photons, or particles of light, travel at a constant rate, 299,792,458 meters per second exactly. Our sun sits at a point 148 million kilometers from us. This means that it takes approximately 500 seconds for light to travel from it to us. So what you see in the sky right now is not the sun as it is, but the sun as it was 8 minutes and 20 seconds ago. This time delay becomes severe even when you consider things that are relatively close to us. The next nearest star, Proxima Centauri, is so distant from Earth that it takes 4 years for its light to reach us. All of this means that for objects that are further and further away from us, we would see it as it was further and further back in time. If there was an object sufficiently far away, we would see it as it was 13.8 billion years ago, near the origin of the universe. And fortunately, as some speculate, We exist in an infinite universe, so such faraway objects should in fact exist. With the James Webb Space Telescope, we hope to be able to see them. But why does the James Webb Space Telescope view in the infrared? Well, one reason is that infrared light tends to punch through clouds of cosmic matter better, allowing us to see past otherwise opaque gas clouds, to see what lies on the other side. But the main reason, and the one that is relevant to seeing those early galaxies, is because of a second quirk of the universe, the fact that space is expanding. For reasons we don't fully understand, but which scientists currently theorize are the result of dark energy, everything in the universe is moving away from everything else constantly. As a star moves away from us, the light from it is stretched in a process known as the Doppler effect. And because the wavelength of light is the part that defines what color we see, as light stretches, it shifts further and further towards the red half of the spectrum. But this expansion isn't constant. Scientists have observed that the further something is away from us, the faster it is expanding away from us too. This means that light from the furthest away galaxies have shifted so far into the red that it has gone beyond it, into infrared frequencies. Hubble was not fully designed to detect these frequencies. The James Webb Space Telescope is. James Webb's receptors can detect light at frequencies from 0.6 micrometers to 28.5 micrometers long. Interestingly, this means that it actually can't see all visible light frequencies. It can see red and a large amount of orange frequencies, but nothing beyond yellow. Its focus lies in the infrared frequencies. In this way, to say that the James Webb Space Telescope is a replacement for Hubble is factually incorrect. At NASA, they prefer to say that James Webb supports and complements Hubble. Each will focus on frequencies of light that the other does not see so clearly. Besides which, as Hubble could potentially last until 2040, it's likely that it will outlast the James Webb Space Telescope too, which would make James Webb an odd replacement. Still, to see these infrared rays from such distant sources is a huge challenge. If you and a friend each held a candle on a clear night and walked away from each other, it wouldn't be too long before your candle started to look dimmer to the other person. This is because of the inverse square law, where light photons spread out with distance. Plus, light tends to scatter when it passes through matter, and although space is extremely empty, there's enough particles of dust floating around that over the vast distances of space, objects that are far away get more difficult to see. To combat this, the James Webb Space Telescope houses a gold-plated beryllium mirror that is 6.5 meters in diameter. This makes its surface area 6 times larger than that of Hubble's mirror. This larger mirror is designed to catch more light from distant sources before focusing it back into the telescope's instruments, allowing them to pick up fainter traces of radiation. Furthermore, as the name suggests, the James Webb Space Telescope is a space mirror. Being in space means that the telescope does not have to contend with the Earth's atmosphere, which can diffract and distort light waves that pass through it. The vacuum of space provides a much clearer view, allowing James Webb to find those tiny diffuse infrared waves much more easily. James Webb will be orbiting the Earth in a position known as the L2 Lagrange point. This position in space is technically not a true orbit, but exists 1.5 million kilometers from the Earth at the point furthest away from the Sun. For point of reference, the Moon is 384,400 kilometers from the Earth, so this is much further out. Due to the way the Earth's gravity interacts with the Sun's, this point of space is gravitationally stable, making it easier for an object to hover there with minimal effort. This makes it an ideal viewing station for an orbital telescope. One spacecraft was sent there already, the Planck Space Observatory. The distance from Earth is far enough away that the James Webb Space Telescope does not have to contend with any radiation bouncing off the Earth or the Moon, but it is also close enough that it can send signals back to Earth telling us what it sees. Naturally, at this position, it will be very difficult for us to visit the James Webb Space Telescope. So, although James Webb was designed with a docking ring, it is currently planned that there will be no missions to James Webb to service or replace its parts once it's up there. Although it needs minimal effort to maintain its position, minimal is not zero. James Webb has enough fuel to maintain its position for at least 5 years and at most 10. After that, it will decay from its orbit and will no longer function. It has a guaranteed expiration date. One final benefit of this position, however, is the temperature. Because heat travels in infrared waves, the heat generated by the telescope's own parts could potentially blind its own sensors if left unchecked. However, thanks to its position in space, James Webb will be able to cool itself to temperatures of -223 degrees Celsius. This is also aided by its solar shield. You have no doubt noticed the large silver canvas at the bottom of the satellite. This 5-layered shield is the size of a tennis court and is designed to point in the direction of the Sun, Earth and Moon to block heat coming from them. With that last fact, you may have begun to realize the scale of this satellite. It is vast, roughly 20 meters by 14 meters, and weighing almost 6,500 kilograms. This raises a question: how are they going to get this telescope into orbit? Well, that is explained by one of the most, frankly, astounding engineering aspects of this telescope: its capacity to fold up and unfold. The Ariane 5 rocket that will carry James Webb into orbit has a 5-meter diameter, but this is not sufficient to fit the James Webb Space Telescope. As such, James Webb has been designed so that its mirror can fold in, as can its solar shield, reducing its total dimensions while it is in the rocket. Once it has been launched, and while it is traversing space to its Lagrange point, the James Webb Space Telescope will begin gradually unfurling in a delicate ballet. Arms will unfurl, shields will unspool, the hexagons of the mirror will rotate into position, and then align themselves with the aid of tiny motors that are perfectly flush with each other, all to allow it to go about its incredibly delicate business of gathering radiation from the dimmest lights in the sky. Mastering this process of getting such a sensitive device into orbit without something breaking is the reason James Webb has taken so long to build. Remember, once launched, there is no chance of going up there and fixing it. If something broke during deployment, it could well spell the end of the entire mission, wasting over 2 decades of work and $9.7 billion. In 2005, just a few years before the initial intended launch date, the entire project underwent a fundamental redesign. Everything was checked and double-checked by review boards. In 2018, the project was further delayed when a test of deploying the solar shield ended up with it ripping. A review of what went wrong found an additional 344 potential single-point failures, any one of which breaking would mean that the entire thing would no longer work. When costs started rising in 2011, the American Congress moved to reduce NASA's budget of a way of cancelling James Webb. However, the public backlash in support of the project ultimately led them to reverse their decision. James Webb was built by NASA in cooperation with the European Space Agency and the Canadian Space Agency. It has been delayed over 13 times. Its project costs have increased from $500 million to $9.7 billion. But finally, very soon, it will be here. Its mission to peer into the heart of space and uncover the mysteries of the formation of the first galaxies, stars and planets will finally begin. You can bet that when it launches from the European spaceport in French Guiana, there will be plenty of people waiting for news of a successful launch with bated breath. And you can also bet that once it's in the sky, scientists will be fighting tooth and nail to get a chance to look through it and to discover what wonders it sees. So, good luck for the launch and the deployment to all the teams involved with this. If it works, this instrument will be the biggest thing for space science for potentially decades to come. This is one of the most hotly requested topics for this channel. Even if you didn't actively request it yourself, you couldn't have missed the buzz around the James Webb Space Telescope. It is more powerful than any other space telescope, including Hubble. So big, it had to be folded up like origami to fit onto the rocket that carried it into space. So precise and sensitive, it has to be kept at temperatures not much warmer than absolute zero to prevent its own internal heat radiation from getting in the way of its sensors. So expensive, it cost $10 billion to make, and so complicated, it took decades to complete. 300 potential failure points stood between it and proper functionality. But now it is here. And it has an incredible mission: to study planetary systems for evidence of life, to understand the formation of planets, stars, and galaxies, and to peer out across the universe to objects so far away the light they gave off has been traveling for almost as long as the universe is believed to have existed. In other words, the James Webb Space Telescope was built to spot the first stars and galaxies at the very edge of our knowable universe, objects from the beginning of time. And the first images have started coming in. I'm Alex McColgan and you're watching Astrum. Join with me on a journey as we look over the early photographs coming out of the James Webb Space Telescope and see for ourselves the power and precision of this engineering miracle. It's already promising to be spectacular. For those who are new to this channel, we've already spent some time watching the James Webb Space Telescope as it's gone from a work in progress to a fully realized piece of hardware. It was first conceived in the 1990s and was originally intended to cost only $1 billion and to launch in 2007. However, numerous setbacks and delays plagued the project, pushing it back again and again. It was only in December 2021 that it finally launched, and it has been spending the intervening months slowly unpacking itself, powering up its systems, and testing its hardware. It is a 6,500 kilogram monster, with a sun shield whose 14 by 21 meter dimensions are around the size of a tennis court. Its mirror for capturing light is 6 times larger by area than Hubble's lens, which allows it to pick up more photons from further away to create crisp images. It boasts numerous cameras and scientific instruments which allow it to see across the infrared spectrum. This is a feature that is vital to its unique mission. Due to the expansion of the universe, all of the light from the furthest reaches of space have been stretched to the point that no matter what they were to start with, they are all at least infrared light now. So the only way to see these light sources is with an infrared telescope. On top of that, infrared is much better at punching through dust clouds and other obscuring debris, giving the James Webb Telescope the incredible ability to see objects that are beyond the sight of Hubble. I compare this telescope with Hubble a lot, as the James Webb Space Telescope was originally intended to be Hubble's successor. However, given their slightly different fields of view, Hubble can mostly see in visible light spectrums, while the James Webb Space Telescope can almost exclusively see infrared and can't see some visible light spectrums at all. It's more accurate to say that the two telescopes complement each other rather than compete. They work together to form a powerful duo, expanding our understanding of the universe. But that's not what you're here for. You're here to see what James Webb can do. Beginning in our own galaxy, let's gradually expand our vision outwards towards the edge of the knowable universe. You are in for some spectacular sights. The first stop on our journey is a place known as the Cosmic Cliffs. The Cosmic Cliffs, otherwise known as NGC 3324, are part of the Carina Nebula, about 7,600 light-years away from us. These peaks you are looking at are massive structures, around 7 light-years high, and what you see here is only a portion of the nebula as a whole. The actual nebula is much larger and contains a hollowed-out center, where the stellar winds given off by stars have blasted all nearby dust away from them. What we are looking at here is the edge of this hollowed-out bubble. Scientists are very interested in this region of space for one simple reason. It helps answer questions about the formation of stars. Thanks to the stellar winds in this zone, dust and matter conglomerate together, forming a birthing place for stars. However, for all our stargazing, there are still many mysteries surrounding this process. How exactly do they form? What do the different stages look like? It's difficult to tell. Part of the difficulty with finding the answers is the dust itself, both vital to the process and also a massive impediment to seeing it happen. It wraps around the forming stars like a protective cocoon, stopping scientists from seeing very clearly what is going on at the moments we'd like to see the most. James Webb fixes that. Not only does this image provide more detail than Hubble's image, but thanks to James Webb's onboard MIRI, or mid-infrared instrument, we can peel back the layers of dust and see what lies within. See how much clearer the image is. This will provide scientists with data on the formation of stars for a long time yet. So much for the birth of stars. At our next stop, the James Webb Space Telescope uncovers more about the end of their lifespan. And for this, let's look a little closer to home to NGC 3132, otherwise known as the Southern Ring Nebula. The image on the left was taken by James Webb's near-infrared camera, while the one on the right was taken by MIRI. This is a planetary nebula, although technically that term is a bit of a misnomer. While regular nebulas are the birthplace of stars, a planetary nebula is not a place planets form. Instead, it was just an unhelpful naming convention used by early astronomers who noted the round shapes of these nebulas and they thought they looked a bit like planets. The name stuck, even though our interpretation of the name has moved on. Planetary nebulas like this one are formed when dust and gas are blasted out from dying stars towards the end of their lifetimes. Knowing the chemical composition of this dust is useful, as understanding what material exists in the universe helps us to understand what later waves of stars might be made of. So once again, James Webb's ability to peel back the layers of dust to see what lies within is invaluable. Compare this with Hubble's image to get a sense of the increased detail that James Webb is able to bring to bear. From this, scientists have learned that the second star within the system still has not actually exploded, so the formation of its own planetary nebula is still likely to come. We can also get a better sense of how the gravitational interactions of the two stars stir the nebula, mixing the dust together in fascinating patterns. Now, let's look a little further out, beyond our galaxy. If we want to see star creation, it makes sense to find a location like this. 161,000 light years away from us lies the Tarantula Nebula, so named because it evokes the idea of a giant tarantula lurking within its silken web. Aside from the obvious otherworldly beauty, this area is of particular note to scientists because of its similarity to a period in the universe's history known as the Cosmic Noon. At that point, which to our best understanding took place about 1 billion years after the universe began, star creation was at its most prolific. It is thought that conditions there would have looked something like this. James Webb has been able to spot stars here that are only just coming into being, a fascinating period of time to study. Let's look further out again. As our gaze extends, we lose track of individual stars and start seeing things on a galactic scale. Even here, there are beautiful dances being played out. Stephan's quintet is a formation of 5 galaxies, although one is not really next to the others, but just looks that way from our perspective. Famous for being featured in the film It's a Wonderful Life, it is thought that 4 of these galaxies will one day collide. Indeed, 2 are already doing so. James Webb allows us to see clearly the brilliantly hot dust being kicked off as these 2 central galaxies circle each other. The gravitational forces here are mind-bogglingly intense, the energy profound. It is a dance that is truly only appreciable at scales like this one. This image was not taken at a single time, but actually is a composition of almost 1,000 separate images that James Webb took and then scientists put together, giving it incredible resolution for picking out details. Let's look further out again, until even James Webb is straining to see, in an image known as Webb's first deep field. This image is taken from an area so small, a single grain of sand held out at arm's length would block it from your view in the night sky. At this scale, individual stars are almost completely absent. Most of what you can see here are not stars, which would be too small to detect on their own, but galaxies. Here you can see the fish lens effects being created by gravitational warping, as relatively nearer objects bend light around them, distorting what lies beyond. We start to see the edges of the universe. In this image is one of the oldest galaxies we have ever sighted. It is so far away the light from it when it was born at the beginning of the universe has only just reached us. Where is it? We are going to need to zoom in. Do you see it? It's admittedly quite small. By evaluating markers within the light given off by this tiny red galaxy, scientists are able to identify how far it has redshifted, and thus how long the light from it has been traveling by comparing it to normal visible light from similar sources. This tiny dot was found to be 13.1 billion light years away. As far as we know, given that the universe is thought to be 13.7 billion years old, this is one of the earliest galaxies that we will ever be able to see. Now, you might be disappointed by how small it is. However, there is some room for hope. Compare this image with one taken by Hubble of the same region. Obviously, James Webb's image is crisper and clearer, giving more detail and showing more objects. But there is one vital distinction between these two images. Hubble took its image by staring at this patch of sky for 10 days, slowly gathering every photon it could from this region of space and compiling them into a single image. James Webb, on the other hand, took only half a day taking its own image. What this implies is that if James Webb was able to take such a detailed image in 1/20th of the time, imagine how detailed an image it could take if it was given a comparable amount of time. In other words, this tiny little dot is likely not the best that James Webb can do. I hope these images have given you a sense of the scientific breakthroughs possible with the James Webb Space Telescope, but also just how beautiful the sights of the universe are. Images like these blew me away. Sadly, we are going to have to be a little patient to see what discoveries James Webb might have in store for us. James Webb has only just finished running through its calibrations, letting its instruments cool off and making sure everything is working perfectly. There are queues of scientists fighting over who gets to use it to do what over the next 5 to 10 years of its expected lifespan. Each second is hotly contested. It will be investigating exoplanets for signs of hospitable atmospheres for life, unveiling nebulae to find the origin of stars, and will help us to understand the difference between an old galaxy like ours and the young galaxies that formed just after the Big Bang. With a tool as powerful as the James Webb Space Telescope, who knows what else we are about to discover? The James Webb Space Telescope has been in space for over a year now. The images it takes of the universe continue to captivate with their high-resolution detail and breathtaking beauty. However, although it may sound counterintuitive, it is often what the Webb does not see that allows us to really shine a light on the universe's inner workings. This seeing without seeing might sound strange, but it's a foundation on which much modern observation of the universe is based. Through clever techniques, it allows us to understand the chemical composition of molecular clouds and nebulae, the makeup of atmospheres around exoplanets, and the existence of rings around asteroids in our own solar system. The James Webb Space Telescope is uniquely placed to take advantage of these clever techniques due to its unprecedented sensitivity and precision. I'm Alex McColgan, and you're watching Astrum. In this second video on the spectacular sights captured by the James Webb, I will show you the awesome power of not seeing, as well as seeing, in helping us expand our understanding of space around us. Let's begin with this image of NGC 346, a cluster of stars and associated nebula found in the Small Magellanic Cloud, 210,000 light years away from us. NGC 346 is interesting to scientists because the conditions and amount of metals found in this area are similar to the conditions back 2 billion years after the Big Bang, in a highly energetic period of the universe's history known as the Cosmic Noon. Countless stars and galaxies were rapidly forming during this point in time. By studying this nearby modern contemporary, scientists can get a better idea of what Cosmic Noon might have been like. But how do scientists know the metallic composition of these beautiful swirls of stellar matter? One method is through looking at emission lines. When gases get hot, say because they have been warmed up by a star, The atoms that make them up seek to dissipate that heat by emitting radiation. However, for reasons that have something to do with quantum mechanics, which we won't dive into here, every atom can only emit radiation at a specific, unique wavelength. This gives elements distinct chemical fingerprints. If you know the wavelengths of light given off by oxygen, you can always tell when superheated oxygen is the source of any light you come across. So, by seeing this light, the James Webb Space Telescope has an idea of the chemical composition of this nebula. The Webb is particularly suited to investigating nebulae like these, as infrared is much more able to pierce dust clouds and see what lies at their heart. Webb's superior sensitivity allows it to detect details that had never been seen here before, including the small disks of dust that were forming around developing protostars, potentially even marking the beginnings of planets. However, these are standard methods of observation. I started this video by talking about seeing through not seeing. And when it comes to astronomy, merely looking at the light emitted by objects is often not enough. For instance, recently the Webb imaged this. This is an ice cloud. More specifically, it is the Chameleon-1 dark molecular cloud, another birthplace of stars. As you can imagine, an ice cloud is not hot enough to radiate light with emission lines. So here, scientists need to use a different technique to learn its chemical composition. But thanks to Webb's piercing vision, a different method can be employed. As I said earlier, when atoms become excited, they release radiation. But this process works in reverse too. When cold atoms are hit by radiation, they can become excited. They absorb the energy, becoming a little warmer. This has a clever implication. It means that if you shine a continuous spectrum of light through a gas cloud and see which frequencies of light get blocked by that cloud, it'll tell you just as certainly what elements make up that cloud as if you'd heated them up and they were radiating. This is what I mean by seeing through not seeing. Of course, it does hinge on light shining through the cloud you want to look at. This occurs through all the stars sending out light from behind the Chameleon-1 dark cloud. The light given off by stars is much more varied in its wavelength than the light given off by specific gases, as solid objects give off photons under different rules to gas. This provides a smooth, continuous light source to check absorption lines. There is a problem though. For objects as large as a molecular cloud, they can be too dense for starlight to be able to penetrate it. This is where the power of Webb comes into play. Thanks to the Webb's unprecedented sensitivity, for the first time, scientists have been able to detect the light from distant stars through the thick cloud of Chameleon-1, allowing them to see its chemical composition. What they found was a surprise. Not only does the Chameleon-1 dark cloud contain water ice, but also some of the fundamental building blocks of life: ammonia, methane, and methanol. This means that stars and planets that one day form in this icy cloud will start off with some quite complex chemicals to get the ball rolling. And if this turns out to be common, it makes it much more likely that worlds capable of bearing life are actually widespread throughout the universe, decreasing the likelihood that we are alone in it. Spectroscopy, the science of studying the chemical makeup of objects from their absorption lines, is a very versatile tool, and it extends to much more than molecular clouds or nebulae. Through it, we can also learn much about the atmospheres of exoplanets. Webb was able to discover the chemical makeup of one such exoplanet, WSP-39b, a Jupiter-sized exoplanet 700 light-years away from us, by waiting until it passed in front of its own star. Light from the star filtered through the planet's atmosphere, where the gases within absorbed the light at certain frequencies, leaving their distinct fingerprints on what remained. Webb detected sulfur dioxide in WSP-39b's atmosphere, the first time this compound had ever been seen in an atmosphere outside of our solar system. Webb also provided a complete breakdown of all other chemicals and elements present, including some water vapor. Spectroscopy, as impressive as it is, isn't the only way Webb makes discoveries by not seeing. There is a second process known as occultation that astronomers have been making use of over the last century. Rather than searching for the spectroscopic breakdown of the light from stars, watching for occultation involves noting a star's brightness over time. By looking out for the sudden dimming of stars, scientists can discern the presence and characteristics of dark objects that pass in front of them. And the James Webb Space Telescope is very good at spotting such dimming moments. In our solar system, between Saturn and Uranus, there lies a rather unusual asteroid called Cheriklo. It is 250 kilometers in diameter and is the largest of the asteroids known as the Centaurs, asteroids that tend to orbit between Jupiter and Neptune. However, that is not its claim to fame. Cheriklo is impressive because in 2013 it was discovered to be one of 5 objects in our solar system to have rings. For a while, scientists did not think that objects as small as Cheriklo could support rings. Even now, they are unsure whether these rings are only here because they are relatively new, forming in the last few million years or so, or whether some gravitational phenomenon caused something like shepherd moons, keeping them in place. James Webb Space Telescope tested its ability to observe occultation by trying to spot these rings as Cheriklo passed in front of a distant star. This was not as easy to do as it sounds. It takes extremely precise predictions to know where Cheriklo would orbit, to know which star to watch. Given the size of objects in space, even the smallest miscalculation would result in no occultation being observed. That said, Webb was able to spot Cheriklo and its 2 rings as they passed in front of the star, noting the occultation of the asteroid itself as well as each of the rings, as seen in this video. The rings were too small to be imaged by Webb directly, but from the sudden dimming in the star's brightness, Webb was able to clearly make out the rings, which are thought to orbit about 400 kilometers from Cheriklo itself. The larger of the rings is only 6.9 kilometers wide, and the smaller one is a tiny 120 meters wide. It is not yet clear what these rings are made of, but Webb was able to detect crystalline water ice on the main body of Cheriklo. With further observations, more information about these rings will come to light. And speaking of rings, there is one more image I want to show you. This is just one that I found spectacular. The strange rings of Wolf-Rayet 140. These reddish purple rings are like nothing I've seen in space before. The astronomers who first saw it thought that something might be wrong with their equipment. The rings seem more like the ripples of a pool or the rings of a tree than an actual interstellar object. And yet, these rings actually represent over 100 years of a truly incredible phenomenon. At the heart of these rings lies a binary star system. Every 8 years, the 2 stars at the center of this system orbit close to each other, and their stellar winds interact in such a way as to blow a fresh ring of dust outward into space. There are at least 17 rings, meaning this process has been ticking along every 8 years for the last 130 years or so. This phenomenon is large. The furthest ring is 70,000 times the distance from the Earth to the Sun. The detail Webb was able to capture is incredible. Previous glimpses at this system indicated that there might have been one ring, but it's incredibly blurry compared to the resolution captured by Webb. These rings were useful for astronomers, as they provided opportunity to spatially document the chemical compositions of the rings of Wolf-Rayet 140 over time. Through these probes, scientists found what they believed to be polycyclic aromatic hydrocarbons. PAHs had been known for a long time. They help with the formation of stars and planets, but their origin has long been a mystery. Now, thanks to this discovery by the James Webb, Wolf-Rayet binary stars have stepped forward as one possible source for this crucial compound. And it was only possible because of the spectroscopy and James Webb's ability to see and not see light in incredible detail. There will no doubt be many more discoveries Webb will make in the years to come. Such a powerful telescope can capture images at far greater clarity than the space telescopes before it. But I thought it was important to emphasize that not all the Webb's discoveries are stunning images in the night sky. Many of its biggest breakthroughs lie in the tiny hidden details of things not seen. Light not appearing when it might be expected to, indicating the presence of hidden chemicals or celestial objects. Because it turns out, it's not always about what you see. Sometimes what you don't see is most informative. Coincidences aren't always coincidences. Imagine for a moment a game of pool. The balls are placed in a triangle, and the pool player lines up the shot. He shoots. The balls scatter, but then, against all probability, they all start falling into the same hole, at the same corner of the table. What would you think if you saw it in that moment? Are you likely to chalk it up to probabilistic fluke, or perhaps some skill on the part of the player? Or are you more likely to start checking under the table that no one's done something to lower one of the legs? Some things in the universe are so improbable, they really shouldn't ever happen. Think now about our solar system, and imagine a large mass came screeching into it, large enough and at just the right angle for its gravity to wobble one of our planets out of its orbit and to scatter that hapless planet into interstellar space, like the balls on the pool table, but a whole lot bigger. What are the odds that that mass would knock out not just one planet, but two? And that those two planets would head off in the same direction at the same speed, enough that once out in interstellar space, they would start orbiting each other. The odds are astronomical, but I suppose it's technically possible. And so it's not a complete surprise that the James Webb Space Telescope has found an example of exactly this going on in the Orion Nebula. In the space between stars, two planets are orbiting each other. Each of them has a mass similar to that of the planet Jupiter, so scientists call them Jupiter Mass Binary Objects, or JUMBOs for short. But the Webb didn't find just one example of JUMBOs, it found 40, representing almost 1/10 of all the wandering planets that Webb saw in Orion. That's not just unlikely, that's downright suspicious. So much so that it's time to start checking the legs of the universe to see what's going on. I'm Alex McColgan, and you're watching Astrum. Join with me today as we investigate JUMBOs and try to find clues to explain just what might have caused such objects to occur so frequently in Orion. One thing scientists all agree on: our models for the formation of stars and planets are certainly wrong. But in what way is still to be discovered. JUMBOs were first seen by the James Webb Space Telescope in October 2023, when it turned its awesome high-resolution instruments on the Orion Nebula. It's possible JUMBOs exist in other places too, but they have remained undetected for now, probably as their relatively small size makes them quite difficult to spot, unless you're using techniques like gravitational microlensing, which is in and of itself a highly randomized way of finding new planets. Gravitational microlensing, or seeing the momentary increase in a star's brightness due to the relativistic effects of an object passing in front of it, bending more of its light towards you, is an event so unlikely that Einstein thought we'd never actually catch it happening in nature, even though he theorized it was occurring. While technology has improved to the level that we can actually take advantage of gravitational microlensing as a way of spotting new planets, mostly by developing some wide-angle telescopes, which you can watch a video about here, you still need a JUMBO to pass in front of a star before you can see it. It's not surprising that relying on such randomness has left a lot of planets slipping under the radar. We need a powerful telescope like the Webb to give JUMBOs a proper look. But when we did discover them, They were a total surprise, one that no one in the scientific community had seen coming. The ones seen by the Webb are relatively young, only 1 million years old, compared to our own Earth's 4.5 billion years. But the strangest thing about them is how they orbit. Instead of orbiting happily around a neighboring star, or drifting through the vastness of space like most rogue planets we've discovered before, jumbos orbit each other. They are binaries, gently caught up in the gravity of the other at a distance of around 200 astronomical units, or 200 times the distance between the Earth and the Sun. Frankly, this is baffling. Binaries aren't completely unheard of in our galaxy. In fact, they are relatively common. About 1/3 of all the stars in the Milky Way are binary or higher, meaning it's quite natural for orbiting bodies to take this configuration. However, the smaller you get for the size of your star, the less this tends to happen. 75% of massive stars are binaries. 50% of stars the size of our Sun are. For smaller stars, this number drops to 25%. And for objects smaller than a brown dwarf, which aren't big enough to ignite into fully fledged stars at all, and are only around 15 to 75 times the size of Jupiter, it really shouldn't ever happen. Jumbos ought to be impossible. There should be no reason their frequency should suddenly uptick to roughly 1 in 10. And yet, that's what the Webb saw. When it surveyed the space within the Orion Nebula, astronomers were excited to spot 540 different planetary mass objects much smaller than brown dwarfs. And of these, 9% were orbiting each other in these binary pairs. 2 were even circling in a triplet, which is really rubbing probability's nose in it. 9% is an astonishing number at this scale of mass. As soon as scientists realized jumbos were this common, they immediately recognized that our models for the formation of planets couldn't be correct, as there are only 2 explanations for where jumbos could come from. The early days of a planetary system are always chaotic. You've likely seen artistic depictions of molten Earth in its early infancy, with comets and space debris raining down on it. This space debris was far more common in the solar system's infancy, when dust coalesced into rocks, then into asteroids, and eventually into planets with enough gravity to pull everything in around them, causing cataclysmic collisions along the way. Sometimes that gravitational pull was such that it didn't smash 2 objects directly into each other, but instead pulled them out of orbit and left them careening into deep space. This can even happen to very large planets if the circumstances are right. For example, it is actually theorized by some researchers that our own solar system used to have one additional gas giant, which was bullied out of our solar system by Jupiter, or possibly Saturn, although the smart money is on Jupiter. Jupiter's gravity was enough to tug on this other gas giant until it was sent spiraling out into interstellar space. We've asked on this channel before whether there might be a Planet 9. We didn't consider that Jupiter actually might have given it the boot long ago. Regardless, the idea of a planet being sent out into interstellar space, even a large planet the size of Jupiter, is not that extraordinary. Indeed, it's believed that wandering planets of all sizes are fairly common. There could be billions to trillions of rogue exoplanets wandering around in the void of space between planetary systems in our galaxy, which, if true, means there are more flying around out there than there are likely orbiting stars. But the sheer number alone cannot account for that 9% ratio, so something else must be going on. But the alternative explanation for the formation of planets doesn't work either. This second theory states that in the aftermath of a large supernova explosion, or through the force of solar winds, hot matter is sent flying in all different directions away from the center of a nebula. Cosmic dust pushed outward this way is also pushed together, helping it begin to coalesce due to gravity and form new stars. But if stars can arise in this way, why not planets? After all, to push enough dust together to make a star, you at some point will have an object the size of a planet, right? But no, not on its own. While this happens in the nurturing planetary disk of a newly formed star, it turns out that without that extra gravity, an aspect of gas physics stops this theory from working in interstellar space, or at least for objects of that size. It turns out that something called the opacity limit puts a lower threshold on the size of objects that can be formed this way without a star. They either come together to form, at smallest, a brown dwarf, or they resist coming together at all. In other words, interstellar dust and gas go big, or they go home. It works like this. All objects have gravitational potential energy. When gas coalesces together due to gravity, it loses that gravitational potential energy. That energy has to go somewhere, obviously, so in nature it tries to radiate away as heat. This is all very well and good when the gas is spread out, but once more and more gas starts gathering in, as you might see when gravity is pulling in material for a planet, then everything gets cloudier and cloudier, or more and more opaque. This actually makes it harder and harder for this heat to radiate away, so instead things stay hot and energetic. This pushes back on any more material coming together. A delicate balancing act is thus reached, where hot gas that cannot quickly cool down pushes back too hard against any gravity for any planet to form. Stars get around this problem by having a little extra oomph in their formation. There is a reason stars tend to form in nebulas. This vestigial extra push is enough to overcome the hot gas's dislike of pulling together. But once you push past that barrier, you already have too much oomph to form just a planet. Now it's a brown dwarf, or something bigger, or nothing. The opacity limit sees to that. Which is why scientists are searching around for an additional ingredient, something that might explain how a jumbo might still form in interstellar space. To me, this explanation seems like the neater one. If somehow you could overcome the opacity limit, you'd end up with planets naturally arising out of interstellar matter. If two Jupiter masses formed close enough to each other, they would drift slowly together and could quite naturally take up orbits around each other with no star required. Nothing about this relies on crazy probabilities, as the first pool table leg planet theory asks you to believe in. There could even be planets smaller than Jupiter masses out there doing the same thing. Two Earth objects, or even smaller, just too tiny to be caught in the Webb's camera. But perhaps an old theory can provide an answer. In 2001, long before we had any idea jumbos might exist, a researcher called Alan P. Boss published a paper in the Astrophysics journal about the way objects slightly smaller than the mass of Jupiter could form from interstellar matter, provided that magnetic fields are active in the formation process, in effect jettisoning out the newly formed planet mass from the growing cloud that was about to become a brown dwarf, leaving the rest of the cloud to continue on its way towards collapse and stardom while preserving the smaller planet intact. The paper admits that it's conjecture and says that more work needs to be done to verify the idea, but I find it intriguing that the sizes in this theory match the reality of jumbos long before we saw them. Maybe jumbos weren't entirely a surprise after all. Is magnetism the answer to jumbos? It's too early to say. All we know for sure is that we know less than we previously thought. Jumbo's existence calls into question our models on the formation of stars and planets, and shows us more research is desperately needed. But then, that's half the fun of science. A theory is all well and good to have, but when you find something that throws off your theory, it's not a bad thing. It's an exciting discovery, and an opportunity to get even better understanding of the reality we live in. What are jumbos? They are strange, Jupiter mass objects weaving a delicate dance on their own through space. But they might also be the key that unlocks our understanding of how stars and planets form in the first place. For those of you that don't know, the James Webb Space Telescope is going to be the successor to the Hubble Space Telescope. An ambitious project, it aims to have a mirror with a combined surface area of 25 square meters, which is roughly 5 times bigger than Hubble's. Developments for it began in 1996 with an original launch date of 2007, but this date has continuously been pushed back. From the time of writing this script, the scheduled launch date is in March 2021. But what's the holdup? What is taking so long for this telescope to get into operation? Well, it's complicated. Literally. I'm Alex McColgan, and you're watching Astrum, and together we will understand why the James Webb Space Telescope is taking so long. First of all, let's have a quick overview to this magnificent piece of engineering. The telescope features 18 hexagonal segments made of gold-plated beryllium. They combine to make a 6.5 meter mirror, the biggest that has ever been in space by a long shot. There is a very good reason for having such a big telescope in space, namely that in the vacuum of space, there is no atmosphere to get in the way of observations made by the telescope. If you have a look at videos taken by ground-based telescopes, you can see that there's a slight wobble to the image. This is due to the heat in the atmosphere, much like if you looked at a road on a hot day. That's not to mention all the dust and other particles in the atmosphere, reflecting and refracting light, which interferes with telescope observations. Technology is improving to counteract atmospheric influences on ground-based telescopes, but you just can't replace actually being in space. The other big reason for having the James Webb Space Telescope in space is that it is an extremely sensitive infrared telescope. And in this way, it is different from Hubble, which is only capable of looking in visible light and ultraviolet. In fact, the James Webb Space Telescope is more like the Spitzer telescope, another space telescope but with a much smaller mirror, only 85 centimeters across. Seeing as any warm object emits infrared radiation, a ground-based telescope would easily have its readings contaminated by nearby objects and the atmosphere. In the vacuum of space, however, the James Webb Space Telescope is protected from the sun by this massive sun shield, which means the scientific instruments stay a cool minus 220 degrees Celsius. Such a big infrared telescope will mean we can look back in time billions of years to just a few 100 million years after the Big Bang. This will give us an insight into the formation of the universe like never before. The James Webb Telescope will also look at individual stars and even attempt to observe exoplanets, specifically to try and see the composition of their atmospheres. They do this by looking at the light spectrum of planets as its parent star shines through the planet's atmosphere. So, what's been the holdup over all these years? Well, the biggest delays were caused by the design specifications themselves. For instance, the mirrors. There is no launch craft that could fit a 6.5 meter wide mirror inside, so the mirrors had to be designed in a way that allowed them to be folded back during launch. This adds a massive amount of complexity to the design, as 18 hexagonal mirrors aimed at an object billions of light years away means that they must be aligned correctly to nanometer precision. As a result, not only do the mirrors fold out once launched, but each mirror can be controlled individually to a very fine degree. The other design challenge with the mirror would have been the weight of it. To use a mirror similar in weight to the one on Hubble would have meant that James Webb's mirror would be 10 times heavier than it is now, too heavy for a launch craft to get it to its final destination. So engineers used a groundbreaking design, a beryllium mirror that is light but also strong, and plated with gold for the reflective surface. Incredibly, with this design, each mirror segment only weighs 20 kilograms. You might wonder then, why don't they always use beryllium? Well, it is actually a very difficult metal to polish, and designers needed this mirror to be smooth to within nanometers. This adds a layer of difficulty to the building process. Beryllium also isn't ideal for reflecting infrared light, but gold is. You may look at these mirrors and think, oh wow, how much gold is on them? Well, actually, not much gold at all, less than 3 grams in total. How did they get such a fine layer of gold on these mirrors? Well, the technique they used is pretty ingenious. The mirror is inserted into a vacuum chamber, and some gold is vaporized into the chamber. The gold in this vapor form fills the chamber and condenses on all the surfaces, including the mirror itself. This gold condensation gives an extremely even finish, something that couldn't be accomplished through any other method. One of the other key design specifications of the James Webb Space Telescope was to be able to view hundreds of objects simultaneously. The way that they will achieve this is through some groundbreaking innovations invented specifically for James Webb. But this technology will go on to benefit many other sectors like biotechnology, medicine, and communication. Specifically, it is an array of microshutters that can measure the intensity and spectra of light from many distant individual objects at the same time. While spectroscopic technology isn't new, the ability to see up to 100 objects at the same time is. This is an example of the data it will collect. Each band is an individual shutter's spectroscopy reading. Each shutter is also amazing in that it is only the width of a few human hairs. More bespoke devices that had to be designed specifically for this telescope were the infrared camera sensors. These are state-of-the-art, the biggest and most sensitive infrared detectors to ever be made. There will be 3 different detectors, each for different wavelengths in the infrared. They are very advanced in that they don't just take one sample per pixel, but several, meaning they can reduce noise and sense if a cosmic ray hit the pixel and can cancel it out. Another design issue they had to deal with was excess heat. As I mentioned, infrared telescopes are extremely sensitive to heat, even heat generated by the telescope itself. There is a radiator designed into this side to enable the telescope to radiate any heat it generates itself, as the instruments need to be cold, minus 220 degrees Celsius cold. One of the instruments aboard the James Webb Telescope, MIRI, requires even colder temperatures. It can only operate at 7 Kelvin, or minus 266 degrees Celsius. This means it needs its own cryocooler, which is basically a pipe filled with cold helium that flows by the instrument from a pump at the bottom of the spacecraft. Pumps are an issue though because they vibrate, so a super low vibration pump had to be developed. The biggest heat source in our solar system though is the Sun, and to counteract this, engineers designed the Sun shield membrane. There are 5 layers in all, each thinner than the width of a human hair, to keep the mirrors cool and protected from solar rays. This membrane means that while the side facing the Sun can almost reach 100 degrees Celsius, the instruments on the other side remain at around minus 220 degrees Celsius. Again, due to launch limitations, the membrane will start out folded away, and when it reaches space, it will begin to pull the membrane delicately out over the course of several days until it is fully stretched out. The membrane is in fact one of the reasons for the most recent delay to the telescope. During the testing of this deployment process, one of the membranes tore. meaning they had to replace it and look into the design to make sure this didn't happen in the actual launch. Because this is the big thing with the James Webb Space Telescope. If something goes wrong, there is no way to fix it once it's in space. So they have to ensure that they do everything within their power to get it right the first time. And with such a complicated design, there is so much that could go wrong. Just look at this launch process for it to get to its final orbital location, which by the way is the L2 Lagrange point behind the Earth and beyond the orbit of the Moon. It's crazy. Nothing has been attempted on this scale before, and I don't know anything that will match it for a while to come. The James Webb Space Telescope is actually built now. Everything is completed. They are just thoroughly testing each and every one of their systems to make sure everything goes smoothly come the launch. Because if this mission is a success, just this one telescope will unravel so many of the mysteries of the universe by itself. Hubble was already a wonder, but this will be a serious step up. You may never have believed it would actually happen, but the James Webb Space Telescope has launched. And no, its rocket didn't explode in a fireball on the way up. But that doesn't mean we are all good to go just yet. The telescope has some risky months ahead of it. Why is that? Well, James Webb has to make it to the Earth's L2 Lagrange point, all the while performing the delicate operation of unfolding itself before it can unfold our understanding of the universe. I'm Alex McColgan and you're watching Astrum. And in this video I want to go through the deployment process of the James Webb Space Telescope and go into the details of how James Webb goes from being in the rocket all the way until its final science-ready state. I hope by the end of this video I've earned your like and subscription. The Ariane 5 rocket is what engineers planned the James Webb Space Telescope around, the rocket being one of the European Space Agency's big contributions to the mission. The Ariane 5 launches by first igniting the liquid fuel main stage and then the supplementary solid fuel boosters. Ariane 5 has two of these boosters, weighing 277 tons each, and those combined with the liquid fuel stage can take the rocket to the edge of space by themselves. Solid fuel is often used initially as while it can't be controlled so easily, it is a cheaper fuel type and good for that brute force initial liftoff. Once the boosters are expended at about 75 kilometers up, they are jettisoned from the main stage, leaving just the liquid fuel engine burning. Liquid fuel is useful because it can be throttled if needs be. About a minute later, the rocket is beyond the Kármán line of 100 kilometers, and the fairings surrounding James Webb can be safely jettisoned. At this altitude there is virtually no atmosphere anymore, so the telescope no longer needs the fairings protection. About 8.5 minutes after liftoff, the main liquid fuel stage is finally expended, and it too separates from the upper stage. The main stage, like the fairings and the boosters before it, will all end up in the ocean. With all that weight gone, the upper stage ignites and gives Webb the boost it needs to get to the Earth's L2 point. Initially, the altitude doesn't increase. In fact, it even dips, as this part of the process is about building speed, and gravity helps with that a bit. However, this is already a potentially risky phase of the trip, as the sun's rays are directly interacting with the telescope here. Although it is folded up, the sun shield is not deployed, and sunlight can reach Webb's delicate instruments here, warming them up. Until the sun shield fully deploys, it's not totally protected. In order to distribute heat as evenly as possible, and to keep the really delicate parts in shadow, this upper stage rotates back and forth by 30 degrees, like a baby in a cradle. Once in position, the flight trajectory takes it up into space. Its speed still increases even as it combats Earth's gravity, due in part to the fact that the rocket is getting lighter with every passing second as the fuel is burning. At 25 minutes in, the upper stage cuts off and there is a 2-minute coasting phase. Here the rocket rotates around in order to perform a collision avoidance maneuver. Webb then separates from the upper stage, and from then it is all by itself. It is very interesting to me that this view of it leaving the upper stage is the last view we will ever have of the telescope itself. And seeing as this has already happened, here's a beautiful shot of the very first thing Webb did, which is its thrusters firing and then its solar panels deploying, which was actually performed slightly earlier than expected. During separation, usually some rotation is introduced on the payload, but this time there was hardly any rotation at all, and the thrusters had to do very little to keep James Webb from rotating too much, meaning it was safe to deploy the solar panels almost immediately. From here, James Webb provides its own thrust. The cradling maneuver continues using these thrusters, regulating the telescope's temperature. To protect the mirrors as much as possible, these thrusters are only located on the sun-facing side of the spacecraft. A day and a half after launch, the high-gain antenna is deployed, and James Webb passes the moon's orbit. At this point, James Webb has already slowed considerably, as it's basically going directly against the gravity of Earth. Just short of 3 days into the mission, the sun shield pallets begin to deploy. This is a very slow process to ensure nothing breaks, and so Webb doesn't start spinning around uncontrollably from the pallet's movement. Almost 5 days into the mission, the tower separating the telescope and the sun shield extends. This is the aft momentum flap. This is a pretty clever fuel-saving idea. The flap will offset the tiny amount of solar pressure pushing on the sun shield's membrane, meaning Webb doesn't need to use as much fuel to combat this pressure and stay aligned. Still on day 5, the sun shield protectors will unroll and open. Now for the really delicate operation. The center booms will extend, and with them, it will gently pull the sun shield membrane open. If you recall, this was one of the tests that failed back in 2018, as the membrane ripped in deployment. These membranes are thinner than a human hair, and once fully extended are the size of a tennis court. When stretched, these membranes will be tensioned, finally fully protecting James Webb from the sun's harsh rays. The sun-facing side of the telescope will get very hot, almost to a boiling temperature, whereas the side with all the instruments will be kept to a cool -230 degrees Celsius thanks to this sun shield. 10 days after launch, the instruments are cooling down by passively radiating their heat into space. From here, the secondary mirror deploys, locking in place. Next is the aft radiator, a passive cooling system that will radiate the instrument's own heat into space. This is crucial to maintain cool temperatures. On day 12, the side mirror wings will rotate and latch into place. 15 days in, the telescope is fully deployed, and it's simply a matter of waiting for the telescope to reach the L2 point and cool into its final cryogenic temperature state. The last operation to complete before James Webb will be operational is the alignment of the primary mirror segments. Each can be adjusted to within nanometer precision, allowing the light collected by Webb to be turned into crystal clear images. After 29 days, there is one final correction using the onboard thrusters to put Webb into its halo orbit around the Earth's L2 point. From this orbital point, the bright Sun, Earth and Moon will always be behind the sun shield, meaning the brightest thing in Webb's view will only ever be Jupiter. Roughly 160 days after launch, the instruments will have cooled down enough to be operational, and any adjustments that need to have been made will have already been completed. From here on out, the James Webb Space Telescope will be collecting science and unfolding the universe. Thanks for watching. I was honestly blown away by all the incredibly kind comments and messages you've sent me, and by the numbers of you that signed up to the Patreon. Like I said in the replies to your DMs on Patreon, everyone here at the Astrum team is so grateful to have such an amazing community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 Patreon member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.